Good morning, everyone. Today we will start with the new method, which is the bilinear transform method for the designing of the IIR filters. So before going to this one, let's go to the previous method, impulse invariance method, which we discussed in our last class. So impulse invariant method, we have seen if we are having distinct poles, then we use this transformation for getting into the for converting the analog transfer function to digital transfer function, right? Now over here we have seen that the relationship between the analog frequency, this omega, which is represented by ohm symbol, and omega, the digital frequency. So that is this is the digital frequency and this is the analog frequency. It is given by omega, which is the analog frequency, is equal to digital frequency divided by time. And we have also seen from here we have deduced that analog frequency is directly proportional to the digital frequency. Okay. And then we have discussed that due to this direct proportionality relationship, we have many to one mapping when we are using impulse invariant method for the designing of IIR filters, right? So this is one of the major problems with the impulse invariance method for designing the IIR filter. What is the disadvantage? The disadvantage is many to one mapping, and this results in the aliasing. Okay. Again, if we look carefully, the impulse invariant method, it is only restricted for the designing of the low pass filter. Okay, I'm not going into the mathematical details of that one, but what happens is that if you look into the Z transform aspect over there, you will find that the positioning of the poles by the impulse invariant method, it is in a region, it is within a circular region within the unit circle, which is given by this smaller circular region, and the radius of this circle is 0.5 with a center at 0.5, sigma equals to 0.5, sorry, real z equals to 0.5. So the coordinates of this inner circle, it is 0.50, and the radius is of this inner circle is 0.5. That's why we get a smaller circle with a with a center at 0.5. So this is having radius equal to 0.5 and a center coordinate of 0.50. Okay. So if you see, when we use the impulse invariant method, our poles are being restricted within a very small area, and because of this reason, what is happening is that it becomes difficult to design the other types of filter like high pass filter, because in our previous classes we have seen that for the development of high pass filters we need to put some poles at the higher frequency region, similar to near to this pi, right? Then we have band pass filter. Similarly, we can see that in we have seen that in band pass filter, it is a combination of low pass filter and high pass filter. But we have seen, just we have discussed that it is not possible to design the high pass filter over here by using the impulse invariant method. Similarly, if you go for the band reject filter, it is also constituted of low pass filter plus high pass filter, right? So again, there is a problem over there. So due to the problem with this impulse invariant method, that it is prone to aliasing, and only a restricted class of filters can be designed. There was a need to develop another transform which is more robust in nature and more versatile in nature. Okay, so that would help us in designing the different types of filters in a proper manner without any hassle. Okay, so due to this reason, this bilinear transform method, it was being developed. Okay, what does the bilinear transform method says? It says that for changing an analog filter which is having a transfer function of Hs to a digital filter which will have a transfer function of Hz, we have to put S equals to 2 by T multiplied by 1 minus Z inverse divided by 1 plus Z inverse. Okay. Now, if you see and compare with the previous one over here with the impulse invariant method, the bilinear transform method equation is a bit complex, but it gives you the versatility to design the other filters. Okay. So let's look into the relationship between the analog and the digital poles. While we are transferring or we are transforming the uh, filters, analog filters to the digital filters using the bilinear transform method. So over here we have seen that S is being replaced with 2 by T 1 minus Z inverse divided by 1 plus Z inverse. Now if you take this T over here and 2 over here, we get St by 2 is equal to 1 minus of 1 by Z divided by 1 plus 1 by Z. Now if you further multiply this numerator and the denominator with a Z term, we get Z minus 1 divided by Z plus 1. Okay. So after that you take this Z plus 1 on the left hand side. So we get St multiplied by Z plus 1 divided by 2 is equal to Z minus 1. Okay. Then what we have done, we have taken all the Z terms on the left hand side and all the terms divided out Z on the right hand side. Okay. After that we have taken this negative as the common sign, and then we have cancelled that out. So that left us with Z minus Stz divided by 2 is equal to St by 2 plus 1. Now taking the Z common from here, we get 1 minus St by 2 is equal to St by 2 plus 1. Okay. So from here we get that Z is equal to 1 plus St by 2 divided by 1 minus St by 2. Okay. However, for the analog domain, we have previously discussed that S is equal to sigma plus j omega, right? Because in the S plane, we are having sigma in the real axis and j omega in the y axis, right? So we just replace this S equals to sigma plus j omega in this equation, and we get this equation, right? 1 plus t by 2 sigma plus j omega divided by 1 minus sigma, t by 2 sigma plus j omega. Then we have taken out all the real terms at one place and the imaginary components separately. So it gave us something like a plus jb divided by c plus jd in this form. Okay. So if you want to get the modulus of this one, So the modulus of this one is under root of 1 plus t by 2 sigma whole square plus omega t by 2 whole square divided by 1 minus t by 2 sigma whole square plus omega t by 2 whole square. So we get this equation of the modulus of z. Okay. Now let us compare the s-plane. This one is the s-plane and the second one is the z-plane. Now if you look over here, what we get for sigma less than 0, your modulus of z is less than 1. So when sigma is less than 0, so this would be say minus of 0.5, say for example, so it would become 1 minus of 0.5 and this one would become 1 plus of 0.5, right? So the lower term, it will be higher. So your modulus of z would be less than 1, right? Similarly, when sigma is equal to 0, both numerator and denominator, they become equal and you get a value of 1. And when sigma is greater than 0, your modulus of z is greater than 1. So what does this say? This says if you place the poles in the left hand side of the S-plane, your poles in the digital plane will be within the unit circle. Then in the second case, if you place a pole on the imaginary axis, the pole will be on the frequency axis in the Z-plane, which is the unit circle, right? And lastly, when sigma is greater than 0, we get modulus of z greater than 1. Okay, that is outside the unit circle. So if we map it from here, left plane to inside on the unit circle, on the frequency axis to on the unit circle, and right plane to outside of the unit circle. Okay, so this also meets the stability criteria for the designing of the filters. Okay, so if you want to design a digital filter from the analog filter using the bilinear transform method, then if your analog filter is a stable one, then what would happen? The digital filter what you will be designing would also be stable in nature, because all the stability criteria of the S-plane of the analog filters would also be maintained in during the transformation process. Okay. So any doubt over here till now? No? Okay, good. Now the second thing is relationship between analog and the digital frequency. Analog frequency will again I have shown that it will be represented with this omega corresponding to the ohm sign, and digital frequency by the W sign. Okay. So we will again start with the transformation equation S equals to 2 by T 1 minus Z inverse divided by 1 plus Z inverse. And since we are interested in the frequency component, what we will do? We will only be taking the frequency components from the S plane and the Z plane. Okay. So in S plane, our frequency component is j omega, whereas in the Z plane, our frequency component is e to the power j omega, and we will just replace it in this transformation equation. So over here, after replacing, we get j omega equals to 2 by T 1 minus e to the power minus j omega divided by 1 plus e to the power, here there should be a minus sign, sorry, okay, minus j omega, okay. So from here, what we will do, we will be taking out e to the power minus j omega by 2 as common factor from the bracket, and we will get it out from both numerator and denominator. So after taking it out, it will just be cancelling out, and accordingly we get e to the power j omega by 2 minus e to the power minus j omega by 2 divided by e to the power j omega by 2 plus e to the power minus j omega by 2. Okay. Now, if you multiply the numerator and the denominator with 1 by 2, we get to this two equations, e to the power j theta minus e to the power minus j theta by 2, which corresponds to j sin theta, and e to the power j theta plus e to the power minus j theta by 2, which is the cos theta, right? So we will just replace this from here, and we will find that there are two j terms which are coming. So we can cancel it both from the right hand plane and the left hand plane and the right hand plane, and we get omega equals to 2 by t tan of omega by 2. On the other hand, if you look into the digital frequency would be given by omega equals to 2 of tan inverse of omega t by 2. Okay. Now we have previously seen that the analog frequency, it may vary from minus infinity to infinity. So let's look over here. If omega varies from 0 to infinity, we are in the region of digital frequency, it would vary from 0 to pi. Okay. Whereas when we talk about analog frequency minus infinity to 0, we say that the digital frequency would vary from minus pi to 0. Okay. Now from here, if we try to map the analog frequency and the digital frequency and look into the relationship, so in the digital frequency, we see omega equals to 2 of tan inverse of omega t by 2. Okay. And in the y-axis we have the digital frequency, and this is the pi, which is the maximum frequency. We are not taking this negative frequency component over here in the analysis. If you take it, it will be in the third quadrant, having a similar profile over here, whatever you are getting over here. In some books you will find that only this figure is given, and in some books you will find that both the positive and the negative frequencies are given. So both are okay. So since we take mostly the positive frequencies, so I am restricting our discussion in the first quadrant analysis only. Okay, I am not taking this one. This would also have the similar profile, and the analysis will be the same. Okay. So when we are varying it from 0 to infinity, if you see, so what the omega digital frequency omega is doing, it is varying from 0 to pi. So if you see the relationship tan inverse of omega t by 2, so whatever the analog frequency you put in over here, what will happen? You will be restricted within the pi region. You will be restricted within the pi region. Okay, because when you look over here, if you get to the something to the infinity also, try to get into some this infinity of the frequency component omega, you will be having some component related to that in the uh, digital domain also, because what will happen? What is tan 0? What is tan 0?
Zero.
Zero.
0.
Zero.
Tan pi by 2 is infinity. Okay. So if you see this angle, this thing, it is remaining within 0 to pi region. Okay, so even for the infinity value of omega, you will be having some values of omega, right? So what does that mean? That means when you are putting this equation over here, unlike in the impulse invariant method where we were having a straight line like this, in this case what we will be having? We will be having, it will be increasing, and then it will start compressing. It will never reach to infinity. So you will be getting a profile something like this. Okay. So what is happening? Due to this equation, due to the incorporation of tan component, what we are getting? We are getting that there is 1 to 1 mapping. There is 1 to 1 mapping. Okay. But it is an 1 to 1 mapping. It is good because it will take care of this many to one mapping, which was one of the major problem with the impulse invariant method. But over here there is another problem, which is the non-linear mapping, right? Now due to this non-linear mapping, what is happening? The frequency component, they are being compressed in the higher frequency region, whereas the linearity is being maintained in the low frequency region. So this non-linear mapping, it is called frequency warping. This is called frequency warping. Okay. And frequency warping is one of the major problems with the bilinear transform method. However, if you want to design any kind of filter, you will be able to design the filters more conveniently, and you need not to worry about the aliasing factor. Now what is this thing? So this frequency warping, for that, if you see, I have plotted one graph, omega t versus omega, and I have plotted another two graphs, this A, which corresponds to omega versus modulus of h omega, and omega t over here. This both the axes are common, omega t versus h of omega. Okay. So if you see what I have done, I am just taking a pieces of the thing from the transformation matrix, and I am trying to plot. So if you see, and I am considering that all the filters, they have this equal height. Okay. Now if you see in analog domain, all the frequencies, they are being sampled and they are maintaining the same weight. Okay, in all the cases in the frequency component. Whereas when I go to the digital frequency, if you see, though I have done equal sampling, or I have taken equal sections of the frequency components in the from the analog frequency component, in the digital frequency, as I am going towards the higher frequency components, the thickness of this frequency bands, they are reducing. Okay, so on increasing the analog frequency, when we go to the higher frequency components, our digital frequency components, they are getting smaller and smaller, and as we go towards the higher frequency components, it will further be smaller. Okay, so over here also, what is happening? At lower frequencies, there is no frequency compression, whereas in the high frequency components, there is a frequency compression. Okay, frequency compression. And this frequency compression, that means you are using a very small part or small area of the digital frequency component, and you are putting in a lot of other frequency components, right? So designing of filters where you have to place the poles in the higher frequency region, it would become a bit difficult process. Okay. And as I was telling, we usually get in bilinear transform method maximally flat transform. However, frequency distribution, it becomes non-linear in nature. So any doubt till now? Any doubt till now? This frequency compression, how it is happening, everyone have understood? Yes, no, कुछ तो बोला. हेलो.
Yes, sir.
या
Yes, sir.
Yes, sir.
इतना टाइम कहाँ से लग रहा है?
Yes, sir.
Okay. So next is our hs equals to we take up some example. So the question is, suppose an analog transfer function hs equals to 2 by s plus 1 multiplied by s plus 2 is given and converted to a digital filter using bilinear transform method. So this is the equation and we just replace the s with this equation. Okay. So then we solve it, and like in the previous case, as I have told, that if capital T is equal to, if no capital T is given, then we will take capital T equals to 1 second and we will put, and you get this equation. So later on you have to solve this equation. I have not solved it completely, so you have to simplify it and bring it in the terms of uh, z inverse and plus z to the power minus 2 in these terms. Okay, you have to simplify it completely, right? Now another type of question you may get, that you are given with normalized transfer function. So normalized transfer in normalized transfer function, instead of hs, you are given with h of Sn. When you have this n subscript, it means that your transfer function is a normalized transfer function. Okay. And if you see over here, we are given with design a filter, digital filter from the analog filter whose normalized transfer function is given by h of Sn equals to 1 by Sn square plus 1 plus 414 Sn plus 1. Okay. The next is the cutoff frequency of 0.4 pi. We have to calculate the we have designed the filter such that the cutoff frequency of, there is a cutoff frequency of 0.4 pi for the digital filter. Okay. So here see the frequency component, it is being mentioned. Okay. So our cutoff frequency, it becomes 0.4 pi radian per second. Okay. And t is equal to 1 second, it is given. So from here we have to calculate omega c cutoff. So omega c cutoff is 2 by t tan of 0.4 pi omega by 2, right? From here we calculate omega c analog cutoff frequency of 1.453 radians per second. Okay. Now post this one, we have to calculate hs. From h of Sn we have to calculate hs, where how can we convert this? For converting this, we have to replace Sn by s by omega c. Now omega c we have already calculated over here, so you have to put in the values here in the equation and then you calculate hs, and after the calculation of the hs you have to replace s with 2 by t 1 minus Z inverse divided by 1 plus Z inverse, right? So after putting that thing, we'll be getting this equation. Okay. So with this, I will stop here. I would ask you to just practice these two numericals what we have discussed, and if you have any problem, just let me know. Do you have any questions? Any doubts? No?
No, sir.
Okay then. So please try to solve these two equations on your own without looking into this solved part. Okay.